All right, you can see the screen. I'll give everybody just a few moments to read through the problem, and then I'll go through a setup. And as you read this note, the note that I put at the bottom, this will be probably a mechanism I'll use on the quiz next week. So understand how that mechanism works too. You'll see like 2A here, and 0 point C is based on this mechanism down here. All right, let's pull up. I'm going to pull up a worksheet so that we can walk through this setup of this problem. All right, so as always, we're going to start with an assemble where you put a find statement. So in this case, if you read through the problem statement that we saw, you can the last sentence of the problem statement says you need to define the input flows of each stream and also determine the weight fractions of water and potassium in the output stream. So what did it say? There's 3 input streams. So you're looking for the I'll call them M1, M.1, M.2, M.3 for the flow rates for the inputs. And then you also need to find the weight fractions of the output stream, I'll call it 4, of water, and the output of the 4th stream of potassium, K for potassium there. So we're looking for streams 1, 2, and 3 flow rates and the weight fractions of water and potassium in the 4th stream. So let's do a diagram real quick. So the diagram, let me go here. All right, so what's the system in this case? The system is going to be the mixer. You've got the 3 streams coming into a mixer with a 4th stream coming out. And then in the diagram, we're going to want to make sure that we identify the stream. So stream 1 and the information that was given in the problem statement here. Then stream 2, which has got the phosphorus and water. Stream 3's got the potassium and water. And then these numbers are according to maybe my student ID, based on that A and C. And then you have the output stream, where the problem statement defined that it needed to be 1 kilogram per minute. Now, sometimes a problem like this might not give you any of these streams, and you would need to recognize that the best stream to do a basis for would be to set stream 4, because all of the unknown weight fractions are in stream 4. And that would then make this whole system linear. If you have a question mark here, then you're going to have equations where M4 is multiplying unknown weight fractions. So it becomes nonlinear. But in this case, I gave you, just because I'm nice, the basis, the flow in M4. All right, so now I will take this.
I had a question. So on the left-hand side, the W of the N for nitrogen doesn't add up to 1 with water.
Right. This needs to be 9, right?
Yeah.
Thank you, Derek, for catching that, the typo. Yeah, they should add up to 1. All right. So now let me capture that image so I can put it into. All right, and then I need to go back to sharing this screen. And then my diagram, I throw it in here. All right, so then we go to the next. After you've done your assemble, you're going to do analyze. So if you're doing this in the in-class quiz, you write this on a piece of paper. You still do the same steps, labeled the same way. Analyze. Assumptions, we're going to assume. So in this case, the question is this open or closed or isolated? So you look at the system and you've got water and other compounds crossing the system boundary. So this is open. And then is it reactive or non-reactive? Think about the system. Is there a generation of any of these compounds or water, or a consumption of any of these compounds or water inside the system? There's not, so it's non-reactive. And then is there an accumulation of any of these compounds or water in the mixer? Whatever comes in is going to come out, so no, this is steady state. Now we need a basis. Like I told you, I gave you the basis this time. Now I might, on the quiz, if I don't give you this number, you could set one just for purposes of doing the calculations. You can set that value, but so M4, M.4 here is going to be equal to 1 kilogram per minute is the basis. Now we also have a lot of given data that needs to be added. Now in MathCAD, I actually like to add it using a table for these kinds of problems. Let's insert a table. And the table is going to have 5 columns and 4 rows here. I'm going to name the components down this first one here. Nitrogen is the first. We got phosphorus. And we've got potassium. And the reason I'm going to the trouble of doing this is because it's actually going to assign variables for me, and it's going to be really nice. Make your programming easier. Oh, I need to put these in. Let's use smaller. Let's use N, P for phosphorus, and then K for potassium, and W for water here. The reason I'm doing that is I'm going to assign index values that are going to make it easier for programming. Equals 3. So I made an index for each of these. Now I'm going to name so this is W1 for the weight fractions in stream 1, W2 for the weight fractions in stream 3 or 2, and then W3, and then W4. I'm going to make a holder variable called unknown equals 0, just for making the table pretty. So now, the nice thing is I'm actually going to assign values for W1, 2, and 3, and 4 just by putting numbers in here. So here now, I'm going to get the numbers from this system here. So W1, the nitrogen in stream 1, is 0.025 here. We know there's no phosphorus in this, and there's no potassium. And now one way to make sure that you don't make an error like I did that Derek taught, you could do something here where you go 1 minus and then that 0.025 to make sure that you've got the right number there. Stream 2 has got no nitrogen. It only has phosphorus at a 0.05, so it's no nitrogen. Phosphorus at 0.05. So when you're setting this up in a take-home in-class quiz, you could make yourself a table like this, or you can assign values, just so I can understand what you're assigning. There's no potassium in this stream, and then there's the remainder of this is water. We can do the same thing with W3, which is no nitrogen, no phosphorus, and 0.05 potassium, and then 1 minus 0.05 here. And then the stream 4, we were told that we want to have it come out at 0.015 nitrogen, 0.01 phosphorus, and then those are the 2 that are defined. Now we need to figure out, to get those, what's going to happen I'm going to say this is an unknown value and this is an unknown value, just because those are my unknowns. Okay, so what are the unknowns? We've got 5 unknowns here. The M1, M2, M3, and then these 2 unknown weight fractions in the 4th stream. So I've got no extra data that I needed, but let's go to calculate now. All right, so now that we have this table, which is now assigned, so I just to show you that I've assigned those values. If I come down here and I say W1 dot, and then in left square bracket, I say capital N. All right, so now, once we have all our given information, what do we set up next and calculate? So now it's going to be, remember, it's the M dot in minus the M dot out plus the M dot generated minus the M dot consumed is equal to the M dot accumulated. So these are dMdt values here with the dot. So because I said it was open, we have to keep these in and out terms. I said it's non-reactive, so it gets rid of this term here, these 2 terms, the reactive terms. And I said it was steady state, so it gets rid of the accumulation term, and that's 0. So now we're going to have this equation, the mass balance equation, is going to be true for the total mass coming in and out of the mixer, as well as the mass of each of the components. So you can set up an equation now for the total and for each of the components. So let's think about the total. The total equation, if you look at the chart, M1 plus M2 or plus M3 is M1 plus M2 plus M3. Those are the MIs, the sum of the MIs. And then minus M dot 4, that's the sum of the outs. Have all got to be equal to 0, the total mass. But now you can also say the same thing for the nitrogen, and you can say the same thing for the phosphorus, and you can say the same thing for the water. So if we go down here and make these equations, now we can make the nitrogen equation basically as the mass dot 1 of the nitrogen plus mass dot 2 of the nitrogen plus mass dot 3 of the nitrogen. So just nitrogen in the first 3 streams minus the nitrogen in the 4th stream has to be equal to 0. But if you look at this, now we've got new unknowns. So how can we replace those unknowns? Well, we know that the weight fraction of stream 1, that is nitrogen, times the mass flow rate of stream 1 is going to be equal to M1N, the amount of nitrogen. So if you take the rate that stream 1 is flowing and it's 5% or 2.5% nitrogen, 2.5% of stream 1 is the mass in 1 of nitrogen. So let's replace these with W1N times M1, M dot 1, and then we do that for each of these terms here. This becomes W2N times M dot 2, and then we get W3N times M3, and then we've got this one is W4N times M dot 4 is equal to 0. So that's the nitrogen. So now we can do, nice thing you can do here, take, copy and paste this down here. Now you can just change these to P, because it's the weight fraction of phosphorus in each of the 3 input streams, minus the phosphorus and so let's move water down a little bit and make a potassium. And then and it's the same with the K, potassium. So if you're in a quiz, you'd just be writing down these 5 equations. That has to be 0. All the potassium in minus potassium out has to be 0. And then you get the same thing here with the water. All right, so there's 5 equations. So did I say there's 5 unknowns and there's 5 equations? And so you'd think that we're ready to go. Except if you look really close, of these 5 equations, there's only 4 independent equations. And that's because if you take all the nitrogen and all the phosphorus and all the potassium and all the water in the system and add those together, so these 4 equations, if you add those together, So basically W1, W1K, W1P, W1N, that sum equals 1, which then just is this total. So you can't use all 5 of these equations. You can only use 4 of the 5 because they're not independent. So now we've only got 4 equations we can use, but we have 5 unknowns. We need 1 more equation. But that can be what I call the sum of weight fractions in 4 is our last equation. That means this column here, basically if you add those numbers up, it should equal 1. So I can come down here and basically say W4 nitrogen plus W4 phosphorus plus W4 of the potassium plus W4 of the water is equal to, not 1. You add those all up and it's equal to 1. So now you've got 5 unknowns, 5 equations. They're linear because I picked M4. If I had picked any one of the others, then you would have unknown weight fractions. The M4 was unknown. You'd have an unknown weight fraction and an unknown flow rate, and that would be a nonlinear, and you'd have to use a solve block. But because I set it up this way, it's linear. So now I can go in here and set up a matrix. So in the quiz, if it's linear, then you need to set up a matrix. So this is a 5 by 5 matrix because we've got a 5 by 5, we've got 5 unknowns and 5 equations. So this is a 5 by 5 matrix. And so now I'm going to pick for each of these columns in here is going to be, so I'm going to call column 1 is going to be M1, column 2 is going to be M2, column 3 is M3. Then I'm going to put W4, let's do the potassium, and then W4 water. That's the order of my columns. And then the equations, I'm going to use now I have to choose 4 of these top 5. It's often good to use these 4 here that have more information in them so that you make sure you have all your unknowns accounted for. Like if you skip out and don't use the water one, you might be unknowns that you lose. So now we're going to fill out this matrix. So if we use the nitrogen equation as equation 1, and the first column is M1, what is multiplying M1 in this equation? It's going to be W1, left square bracket, N. That's just basically pulling the number from the table and putting it right into the matrix. And it's nice because you can see the pattern if you use it this way. If you put numbers in there, it's really hard to see the pattern. You'll start seeing the pattern fall out when you do it this way. All right, so let's see. The first equation, second column is M2. So it's a W2 nitrogen is multiplying M2. And W3 nitrogen is multiplying M3. And the next row is not M4, it's W4K. What is multiplying W4K in this nitrogen equation here? There is no W4K. So that is a 0. Now, I'm going to put 0, but you have to notice that this equation here has units. This unit for each of these terms is mass per time. So we need to put in here 0 mass per time. So let's put grams per second. And then there's no W4, because W4K and W4W have no units. You need to have units down here. M1 has units of mass per time. The weight fraction doesn't, so that you don't need to put one here because the M1 already has units. So there's no W4W, so 0 grams per second here. And now we do the next equation. What is it? It's the phosphorus. So you'll see the pattern already starting, right? What's multiplying? W1 phosphorus, W2 phosphorus, W3 phosphorus, and then is there any K or W in the phosphorus line? No. So it's 0 grams per second and 0 grams per second. If we go to the potassium equation now, we get W1 potassium, W2 potassium, W3 potassium, just going through and seeing what's multiplying what in the equation. Now this one though, there's a W4K. There is a W4K here, which is an unknown. What's multiplying that? Well, it's a negative M4. So here, there is a, this is going to be M dot 4. And M dot 4 is a known. You can't have any unknowns in this matrix. But you'll notice that M4 was defined right here, M dot 4. So M dot 4 goes there, but it's not M dot 4, it's minus M dot 4. Because this is minus M dot 4 is multiplying W4K. Then, is there anything multiplying W4W? No, not in the potassium line. So that's 0 grams per second. Now, what about the water line? W1W, the capital W I made it, and then W2W, W3W, and then here in the water one, there's no potassium term, so this is 0 grams per second. And then this one here is minus M dot 4, right? Multiplying the W4W. So this is, okay, so now the last equation is this sum of weight fractions here. What we need to do is, we know that this is known and this is known. So the unknowns are W4K and W4W. So that's these last two. But the units on this equation are unitless, you'll notice. So if we go over here, W4K, there's a 1 in front of it right there. So that's 1. And then there's W4W, there's a 1 in front of that there. Okay. But what about in front of M1, M2, and M3? There are none in here. So you can imagine it's the equivalent of saying something like this, M dot 1 times 0. But that 0 now, because this has units of grams per second here, then this 0 better have the units of seconds per gram, so that this term goes to 0 here. Basically, that's what I'm putting in the table right here, is this right here. So M1 is this. I have to put in here a 0 seconds per gram. So then I need to do the same. There's no M2, 0 seconds per gram, and then 0 seconds per gram here. So now I've got my matrix that basically defines these equations with these 5 unknowns. Then we need our B vector, which is going to be a 5 by 1, with what's on the the right side of the equation over here in this matrix. So here, this first equation, there's unknowns of M1, M2, M3, but this term here, you'll notice that these are all known. We know what the weight fraction of nitrogen is in flow 4, and we know the flow rate in flow 4. So this term here is negative on this side of the equation. We put it positive on this side, and it becomes the term over here, W4N times M dot 4. So the first term here is this term brought to the other side of the equation. Then over here, we know WP4 and we know M4. So this whole term moves to the other side of the equation. Now these M1, M2, and M3 are all unknown, so those are in the matrix. This term moves over here. So we get W4P times M dot 4. And it's positive here because it was negative on this side of the equation over here. Then this next one, M1 is unknown, M2 is unknown, M3 is unknown, W4K is unknown. So nothing moves over to this other side. This is a 0. Then on this next equation, the M1 is unknown, the M2 is unknown, the M3 is unknown, the W4W is unknown. So there's none of these terms can move over to the other side. We get another 0. Now on this last one, let me get rid of this term. It's because it's 0 basically. This is known and this is known. So these two here need to move to the other side of the equation. So the other side of the equation here is going to be 1 and then minus the W4N, because it's known, minus W4P. This is unknown and this is unknown. That's why they're in their columns in this matrix. All right, so now you've got, this is the setup.